talk I'm about to give is, and I've just noticed I actually left the word cats off the beginning, unfortunately, but this is using the cats.mtl library, which is, I think I'm 0.8 at the moment. So this is monad transformer library, and this is about dealing with your stacks of monads and handling the effects inside your programs. So I'm going to begin by just going through the general effect cases that they have and the abstract type classes that they use to model these. So I'll start off with funct arrays. So this is when you want to handle errors. And this is the generic type class pattern that they provide for us. So what you get here is the ability is that you can specify an unknown kind of monad high kind of type here. And we don't necessarily need to know what it is. It could be an either, it could be an XOR, it could be an old school valid, it could be a bunch of things. It doesn't matter. We're in some kind of monad space, probably a stack. So probably the error is going to be somewhere in your stack. But what we're concerned about is the functions that we can interrupt with that stack. Primarily with error handling, we're looking at raising an error. So if we look at the implementation of this, we want to write a class that surfaces or provides a way of injecting an error into our workflow. So here's a very simple implementation. So we have the type class of funct arrays in our class. And then this gives us the ability, by implicitly grabbing this type class, to raise that error. And it will go into our monad stack. Now funct arrays only provides a limited set. It's not even a full functor. It just provides these methods, and it can give us the functor itself if we want to use it. But here I also want a pure option. I want a success case. So I'm going to introduce the applicative as well. So I've got the option of returning a correct result. And here's a test. Creates that. I'm going to use the either in this case, and it gives me a failure with the left of the either. So the next one, its common use, is the kind of writer style, and this has been broken down into the functor tell. So this is where we can tell some log information into our workstream, into our program. And there's some other helper methods, basically, effectively very similar. And so here's another example. So I'm dealing with, I want a collection of events. So my functor tell is going to chuck in, it's going to collect events through my stream, through my program. So here I am, again also, because I'm doing some flat mapping operation, the functor tell is not sufficient. So I want to also get a monad as well, so I can do this flat mapping. So the monad gives me the ability to inject some kind of pure value. And now I'm going to put in some logging information, and I've got the value found. And then I'm going to put an event in that something's going to happen after that, or that event's going to get handled. And we can see when we run the test that what we get is this composite vector with my info and my event. And MTL provides these implicits that will automatically, for the writer monad, get me the functor tell type class. And as well with other cats, we can also immediately get the monoid, which will enable the vector to compose. And so that we get one simple vector. Now, if you look here, I'm dealing with a lot of implicits. It looks really ugly. So, and also, passing this vector is quite ugly. You might want to, when you start using this, if you ever go down this way, is write your own kind of methods that you can import into your program. So just a simple pure, so I don't need to use implicit. It will just look for an applicative. A publish, for example, so I can just grab an event, a single event. I don't need to deal with creating a vector. Or a failure for the other case, where I can pass in one failure or many failures. Next, we're moving on to the reader case. Applicative ask, so it breaks down as an applicative, and primarily the ask and the reader method. So when we want some environment to come into our program, that's going to get provided for us. Another example, implicit applicative here. Now what's quite nice with the reader method is if we're doing something very simple, we might not need a monad or an applicative, because the reader method just means we can take our environment and straight map it into a result. So that's quite handy. And a simple test Finally, we've got the monad state. So this is where we want to pull some state into our stack, and you've got what you'd normally expect: getting the state, setting the state, doing something with the state, or modifying the state. And here's an example. We're doing an operation where what we can do, and what I'm illustrating here as well, is the monad state comes with a monad in it. So we don't actually have to pull the monad in here. We can implicitly extract it from the monad state type class. And then we can do a flat map operation and do some state operations here. So when it comes down to it, when we're writing a very complex program into some kind of complex service, we might want a whole bunch of different composable aspects. So here we've got a connection string that we want. We've got some state, maybe we're caching some information. We're going to have some events going on as well, maybe some logging. And we want to handle some errors. And finally we want to tie it together with a monad because we're probably going to do some flat mapping. And so that's a lot of power that's now been introduced to our service. And when we look at this, we actually get some insight into what that service behavior is going to be, or at least some of the things it's going to do. One of the slight things with the functor raise is that it doesn't handle errors. It can only raise them. So there is, and this exists in the original cat library, this error monad or error applicative, and this gives us the ability to raise, or to handle errors. The one problem with this is, unlike the MTL libraries don't interfere with each other. They're a minimum set. So that even though these two are like, say, functor tell and functor raise, they're not actually functors, so you don't get any implicit clashing. With the old error monad, it's actually a monad, or the applicative is actually an applicative. So it will clash if you decide to introduce a monad. So you don't need to have the monad if you're going to use it. And because it's the only one in this collection, it's not a problem. So when you do this, it's now if the applicative asks, for example, actually had to be the applicative, then they'd clash. But you're pretty safe using just the monad error because it's the only one that does this. So using these kind of concepts in these architectures, I actually started out doing this, and I first did my first talk on this in 2014 around abstracting higher kind of types. And a lot of this was, I was kind of motivated by it because they kept changing what the validation monad was, and it was really kind of frustrating. I'd write code, and it was like, you used to use an either. Oh no, we've got a try. Oh no, we've got a validation monad in Scala Z. And I was like, well, why don't we kind of try abstracting this? And when I kind of started down this route, I didn't really know what I was doing, and all I really knew about was traits. So this was really ugly. So I had a new approach a couple of years later, using type classes, and very similar to a lot of the stuff in MTL. And I'd created a particular service and would use natural transformations to move between these stacks. But you've seen the separation that MTL offers, the non-clashing between the tell and the ask, etc. Back here, we didn't have that separation. So you had to create, for each kind of stack combination, if you want to write a valid or you wanted to write a reader, you had to construct them uniquely. So this became a combinatorial nightmare, especially with natural transformations. It was just a lot of boilerplate. I also tried to introduce a way of future handling with future T's, which, when I ever mention this, I don't know if you looked at it, I often get told off because they're not very functional. They're quite ugly. But everything worked, and we've actually had it in production for several years now. And here's where I did a talk on it. So if you want to check it out, and I go a lot more into the architecture and some of the approaches used. What this looked like, if you were thinking of composing a service with dependent services, is something like this. So let's say we've got a service node here, and this service might be going to a database, getting some data, and it uses the reader monad. So it's explicit. This service will run in the reader space. This one here, maybe we're caching some information. So it will use the state monad. And the service would get constructed by using some natural transformations to bring them into a common monad stack, reader, state, error, because this service component with these dependencies had some validation going on. Now, talking about MTL library, very similar, except now the MTL library provides automatic implicit construction of your stack behavior. You don't have to have any boilerplate. It does it all for you using Haskell layered kind of techniques. And instead of having this breakdown of this is going to be a reader state, now we're going to combine them, you can make your whole service architecture, when all integrated, all your dependencies integrated, exist in the same monad space. I'm just going to say all my services are going to run as a complete monad stack. So as an example, here we've got one service. This is a repository, and it's going into state. So it's going to look up a person, and I can get or I can add a new person. And what we've got here is a role access service, which can throw an exception, or capture some kind of validation failure. So I'm going to check someone's role, and if their role's not accepted, I'm going to return a validation failure. So two services, and now my root service with those as dependencies come in here in this monad with M, and it's only concerned about monad error. And now it will call each of those services to give me my end result. So in this case, can a user access? Here's the user ID. I'll go to my repo, check that. I'll then go to the person. This service is only concerned about error handling. It doesn't know about the reader. It doesn't care. It will raise an error if something goes wrong. Otherwise, it will return the result. And here's a simple test, importing all the necessary from cats. But I can actually now construct this service, pass it some initial state, and return a result. And what's really nice is the service is purely functional. So I can just construct it once. In my test suite, I never need to construct it again. It's only the effects that change. So it becomes really elegant to work with. One thing I'd like to point out as well, here we're using funct arrays, here we're using monad error, but the type derivation all works out. The MTL libraries will get the relevant type place, they won't clash or anything, it'll function perfectly well. Now, sorry for that. So, with using these monad structures, they can limit your design in some way, or at least inform it. What I mean by this is, let's look at a return type of when we've got a stack which involves using a valid monad. So, here's a return where I've got either my monad, and this is a state case. Here's my new state, or my result. So what this means is, somewhere in my stack, if I get a validation failure, and a previous operation changed state, or maybe it wrote something to a writer log, that gets dropped. It's completely gone. So when you're building these services, you need to think about what's going to happen with the behaviors of your monad stack. So the moment I've reached this failure, all my work is now gone. Nothing's happened. This can be ideal. Maybe you wanted to raise an event and suddenly you got a validation failure. Well, maybe you don't want that event to go through. Maybe you don't want that state change to go through. But you've got to be aware that this is going to happen. The monad stack does affect the behavior of your program. So that in mind, what you could do effectively is maybe uplift, for example, your validation failure. You could pull it back out of the stack so your flow's not interrupted. You can keep moving. The errors, the log's not lost. The state change can still happen. That's one option. Or you could even change the behaviors of your monad stack. You could actually have an error which also has the log on the left-hand side as well. So another thing it can do as well is when you start building up a service, you're constructing something quite complicated, is you might want to think about, for example, you've got one part of it, a function, that has some I/O operation. You've got another function part that has like a bit of reader operation. Often that can be a good marker that maybe you should abstract that out and make that into a dependency. The reason being it will then make it much easier to test as well. So it can be a good guideline that if you've got too much kind of effectful behavior going on in a single service, you might want to think about abstracting it, particularly when you've got I/O kind of related functions, either the I/O monad or maybe a reader which is using like something more I/O related, like a connection. Another thing that starts to happen when you start to build massive kind of complex services in this way, and very abstract, is that you might have two services that independently have different state, but you've only got one state monad. So you've got like a left-hand state service, the dependency, which say in this case requires a map of string to string, and you've got another service dependency which requires a map of string int. How do you deal with this? Ultimately, you're looking at something that will carry both states. But this gets tricky with your implicits, because how would each service know how to extract its state in this process? So what you can start to use here is a bit of Shapeless. And because you've got all the type information, as long as your types and all of your state elements are separate, map string string, map string int, they're different, we can use the selector and the replacer object from Shapeless to look through that type, and what it can do is it can take this full monad state object here, M and S, where S is the product, the full set, and just give us a monad state type class with just that individual element inside that tuple. And the same for the applicative ask as well, so the reader state. We can just use the selector to just pull out what element of the tuple we need for that particular service. You can probably, now this is as far as we've got, as far as we needed to do, you could probably do similar things for the writer if you've got different logging types, or possibly even the same for the error monad if you've got different types of failures. Now, in trying to solve this problem, we couldn't do it absolutely implicitly. We started getting divergent issues. So what we had to do is, in scope, you'll notice here, these aren't defined as implicit. So when building everything, what we need to do is actually construct it. So here I'm going to do the left-hand side, the map string int, and here I'm going to do the map string string, and then make that implicit, and then that would pull those in. I put a Stack Overflow on this to see if anyone could solve it, and we've had a little bit of a play around with it, but haven't actually come up with a solution. So if anyone can solve it, you could put your solution here, and that would be great. Another thing that starts to come up is when you've got a dependency, which actually requires, I guess, a provider pattern for this. So I want a repository, but that's a conditional repository. I want, in this case, we have a tenant-based system, and what we wanted was a repository for just that tenant. So you can actually do some clever stuff where your service is coming out in that monad space, but that service itself operates in that same monad space. So here we get a function where we're grabbing the service, and then we're calling an operation on the service. And this is something we're just starting to explore now. It gets somewhat tricky to test, especially if you want to do some test cases where, say, in normal case, you might want to do this with a database, but in your test cases, you want to use a state monad. How do you surface that state for that embedded service? And that's something we're playing with now. James, one of our guys here, he started to come up with a kind of a localized implicit process to deal with that. So often one of the big things you hear about when you start using these stacks is what's the cost? You know, you've got your entire service architecture, and every step in your for comprehension is wrapping something in this massive monad stack. So let's have a little look at it. Here are some really ugly, simple test cases. So what we've got here is a baseline case of just creating a whole bunch of objects and doing some operations with them, just addition. And over here, kind of wrapping them up in a for comprehension, putting them into a monad to then give the same kind of result. So our baseline, the non-monadic case here, running 1,000 times, we get 0.1 milliseconds. Now, looking at our monad case, we see an immediate jump. There is a price to pay, even just using the identity monad, which isn't something that even really exists. But it still has to do some boxing. So there is a cost for this boxing going on. When we actually introduce, say, an actual monad into here, because we've got a program, we want to have handles and effects, there's a little bit more of a cost there as well. But now look, we've got our absolutely complicated program, which handles readers, it handles environment, we've got state going on, we've got logging. That's really getting quite expensive. 8 times. So one of the things we can start looking at is, I don't know if you've seen in the cats library, they've got the reader-writer state monad. Now there's not much, from what I can see, not much support for that in terms of all the MTL constructors. But what you get here is, it runs, if you can see this, it's like a combination of a whole bunch of critical monad structures in one structure. So you're not getting this transformer nested objects going on here. So that cuts down a little bit of performance. Here's a case where to get the same kind of, and this is really actually quite interesting, to get the same kind of level of stack here, the 4 stack, we now make the reader-writer state either. And actually it's quicker. The reason for that is the reader-writer state default uses the eval monad. So does the state. If you use the state monad, it's actually a state transform with the eval in it. And the eval is really expensive. The eval is very handy, it helps with trampolining, solves those kind of stack problems. But if you don't need it, you might want to avoid it because you can see the cost of it here. So one thing I started to play around with when I was looking at optimization was, again, like the reader-writer state monad, was to create a service monad which combined the reader-writer state and either, or error monad, all into one simple data structure. No eval. And so it's a little bit quicker than the transformer here, because we've dropped down, we've combined the either into our core data structure, so we save some performance. And then on Friday, I played with an idea of what if we created what I've just temporarily called an unstacked monad. So this has all the functionality of the stack of 4 there, but more performance gain. And what this looks like is a general trait where you've got a minimum set of case classes to hold the particular values. So we've got the error case, just needs to be the error. We've got a pure case, nothing else going on, we've just got a result. We've got a writer case, so it's like the pure but with a log. And finally, and this is where it gets a bit interesting, is we have a function case which takes the reader and state, and this goes to any. And that any can either be the successful return, which is new state, log, result, or a failure, or something else. And there's something else just being actually the case A. The any is because it saves us writing a case class for a simple return. So that reduces an object. And because all our services, they've already been type validated. The moment we introduce our stack, we don't actually need type surety. We know that it's going to be one of these 3 cases. We don't really require creating a new case class just to make this type safe. It's because you're not going to see it. We've already got type safety. Sorry, I think there might have been a glitch there. So, finally, futures. So often when you start using cats libraries, futures just don't seem to appear anywhere. They tend to be discreetly pushed to one side, told they're not really functional, no one really likes them. We've got libraries to work around them, cats.io, things like that. But often in a lot of your projects, we use futures a lot. You know, we don't necessarily just want to throw out actors yet. We might be using streams. You know, how do we get this comfortably into our program? And so I'm just currently experimenting with things at the moment. I've worked those in. And one thing is, in the cats.io, they've got this idea of lift.io. Here, I've introduced an idea of lift future. So we take a future and we put it into our stack. And so here's an example, just using Akka HTTP client, where we do a request and lift that future, get a value, and then lift the future of resolving the content inside that request. We don't make it immediate evaluation as well. That just makes it a little bit more functional, because one of the problems with futures is the moment you create it, it starts to evaluate itself, and that's not very functional. We want to make sure a run operation has actually occurred to kick off this future. And then going back into this unstacked idea is to create a new type of future return. And so we can introduce futures into this unstacked monad as well. And again, it's caused by running a function. So we're not evaluating the future immediately. And another thing, finally, we can start to do is if we want to, for example, lift our monad, this is just another example really, into an actor. We've got our program, we know an actor is going to be there somewhere, we just want to arbitrarily lift it into this actor space. And as long as we've got an implementation of our monad of a lift future and a monad, and we've got some sort of effect, because there's not much point lifting into an actor unless you've got some effect evaluation going on. So we're going to produce an effect evaluation to reduce our stack. So the effect may hold some state. It may provide a connection. It could do a bunch of different, whatever, effectful operations. So then what we can do is we can call our method and run an effect on it. And then down below, the service with its apply method can just use the lift future and the monad operations to wrap everything up nicely and give us something of this new monad stack in the space of n. So I've had to go through things very quickly. I hope this made some kind of degree of sense.